Hi everyone, my name is Batu and I am a software engineer working on real-time embedded systems. And this is an STM32F407G discovery board. It is now running an 8-bit integer neural network classifier as a preemptive FreeRTOS task. The worst case execution time across 1000 runs under scheduler competition is 786.89 microseconds, which I measured using the ARM Cortex-M4's data watchpoint and trace cycle counter. I want to walk you through every design decision that I made in this project, from model architecture, training, and quantization, through Xcube AI's code generation and memory analysis, to the FreeRTOS task architecture and the measurement methodology. So let's dive in. Before getting into the details, let me give you the overall picture of what happens in this project. The project is divided into two sections. The first half of it runs on my laptop. I train a small neural network to recognize human activities from sensor data. Then I shrink it down using quantization so it can fit on the STM32 microcontroller. The second half of the project runs on the microcontroller itself. I take that quantized model, generate seed code for it, embed it in the FreeRTOS real-time operating system with competing tasks, and then I measure very precisely using hardware counters how long each inference actually takes on the hardware. So the overall flow is train and quantize on the laptop, and then deploy and measure on the STM32 microcontroller. Let me take you through each step. Let's start with the data. The dataset comes from the University of California Irvine's machine learning repository. It is called Human Activity Recognition using Smartphones dataset, and you can find a link from my GitHub README document. The model classifies human physical activity into 6 distinct classes, which are walking, walking upstairs, walking downstairs, sitting, standing, and laying down. But how does it actually do it? The dataset was recorded from 30 people wearing a smartphone on their waist, using the phone's accelerometer and gyroscope sampled at 50 Hz. Each 2.5 second window of motion is already pre-processed into 561 features, which include statistical and frequency domain descriptors of the movement. So we have 561 features in a sample, and each 561 feature sample is labeled with one of the 6 classes. The neural network that I trained actually learns the relationship between these inputs and outputs. I picked the pre-computed features on purpose rather than using raw sensor signals because it gives me a fixed length input every time, so there is no variable signal processing on the chip, and the memory access pattern during inference stays completely predictable. And that predictability matters a lot when you're trying to measure the worst case timing. The hardware that I'm using has an STM32F407 VGT6 microcontroller unit, which incorporates an ARM Cortex-M4F processor running at 168 MHz with 192 kilobytes of SRAM and 1 MB of flash. The F suffix means a hardware floating point unit. The chip also has DSP extensions with SIMD instructions, which stands for Single Instruction Multiple Data, and this allows the 8-bit integer inference kernels to process multiple multiply-accumulate operations per clock cycle. One thing this chip does not have is a data cache, and when I first thought about that, it seemed like a limitation, but it turned out to be one of the most important properties for what I was trying to measure. Every memory access is hitting SRAM in a fixed, predictable number of cycles. Therefore, no cycle miss variability is introduced and no warm-up effects occur. I will come back to why this matters when we get to the timing results. So the question I wanted to answer wasn't simply whether the model fits. The memory analysis shows it does comfortably fit on the microcontroller unit. What I was really after in this project is whether inference latency under a preemptive scheduler is deterministic enough to support formal deterministic timing guarantees. This project answers that through hardware measurements. Let's get into the model architecture and training now. The model itself is intentionally simple, a fully connected network with 3 layers built using TensorFlow and Keras. In the code, it's just a sequential model, 561 inputs down to 64 neurons, then to 32, then to 6 outputs. Between the layers, I use ReLU activations, which simply zero out any negative value and pass positive values through unchanged. That nonlinearity is what lets the network learn complex patterns rather than just linear relationships. The final layer uses softmax, which converts the 6 raw output scores into probabilities that sum to 1. So the highest probability is the predicted activity. There are about 38,000 parameters total, and almost all of them are in the first layer. For training, I used NumPy to load the dataset, and Keras handles the rest. I compiled the model with the Adam optimizer and sparse categorical cross entropy loss, then call fit for 15 epochs. I set a fixed random seed across NumPy, TensorFlow, and Python's random module, so anyone who runs this is going to get exactly the same result. Training takes about 15 seconds on my laptop, and the final accuracy on the held out test set is 95.15%. Now, this trained model stores everything as 32-bit floating point numbers, which makes the file about 479 kilobytes. The microcontroller has 1 megabyte of flash, so that's almost half of it just for the model. It's too big and the execution will be too slow without compressing, so the natural next step is to quantize it. This compression step is called quantization. What it does is convert every rate from a 32-bit float into an 8-bit integer. You lose a little precision in this step, but you gain enormously in size and speed, and on a chip with integer SIMD instructions, the hardware is exactly good at 8-bit math. I use TensorFlow Lite's full integer quantization. The key part is calibration here. I feed 100 real training samples through the model, so the converter can measure the actual range of values in each layer and pick the right scale factors. If you get that wrong, you lose accuracy, and get it right, you barely lose anything. And that's what happened in my case. The model shrank from 479 kilobytes down to 42.5 kilobytes. This is about 11 times smaller, and the accuracy only dropped by 0.17%, from 95.15 to 94.98. That quantized 42 kilobyte file is now going onto the chip. Next, to get the model onto the STM32, I used ST's Xcube AI tool. It takes the quantized model and generates optimized C code for it. But before I write a single line of my own application code, it also tells me exactly how much of the chip's resources the model will need. So the numbers are 51 kilobytes of flash total, which is the weights plus runtime library, and only 4.24 kilobytes of RAM. That's 5% of the flash and just over 2% of the RAM, which means there's a huge amount of headroom left for the operating system and everything else. Each inference is about 38,000 multiply accumulate operations, and 94% of those are in the first layer, which is no surprise because that's where the 561 inputs gets processed. One more thing I did before deploying is I validated the generated C code against the original model on my laptop, running both on the same inputs. They matched with 100% agreement and near perfect numerical similarity, so I knew the code generation itself introduced no error before I ever touched the hardware. Now the interesting part is the real-time side. I didn't want to just run inference in a loop and time it, because that's not how real-time embedded systems actually work. In a real-time system, your inference task is competing with other tasks for the processor time. So I built 3 FreeRTOS tasks at different priorities to create that competition on purpose. The first task is the SensorTask at the highest priority. Every 100 milliseconds, it loads one real test sample into the model's input buffer and signals that data is ready through a binary semaphore. It cycles through 12 samples, 2 from each activity class, so all 6 activities get covered. Because it's the highest priority task, it interrupts everything else when it fires, which is exactly the competition I wanted. The second task is the InferenceTask at normal priority. It waits for the sensor's binary semaphore, then runs one inference when data is ready. To measure the timing precisely, right before and right after the inference, it reads the hardware cycle counter. Then it sends the cycle count of the third task through a queue. The third task is the logging task at the lowest priority. It collects all the cycle counts and keeps running statistics, minimum, maximum, and everything needed to compute the average and standard deviation across 1,000 runs. For the actual timing, I'm using the data watchpoint and trace, or DWT, cycle counter, the unit that is built into the ARM Cortex-M4. It is a hardware counter that ticks once every processor clock cycle. At 168 MHz, that makes one tick every 5.95 nanoseconds. To turn it on, you just need 3 register writes at startup. And this resolution really matters. The operating system's own timer, which is a software timer rather than a hardware timer, only ticks once per millisecond, so it literally cannot measure a 786 microsecond event with any accuracy. On the other hand, the DWT can easily measure it down to individual clock cycles. And the measurement window is clean by design. The counter is read immediately before and after the inference call, and the higher priority SensorTask can only interrupt between inferences, never during one. So I can ensure that I am measuring the pure inference time, no scheduling overhead mixed into it. Now, I am building the project and flashing it onto the board. About 106 kilobytes written and verified. And there it is. The green LED toggles on every inference, and the orange one every 100 inferences as a heartbeat. Real activity data are going in, real inferences are running, real measurements are coming out right now. I set a breakpoint that fires once the 1,000 measurements are done. The board runs for about 100 seconds, one inference every 100 milliseconds, and then it stops. Here are the results, which I am reading straight out of the chip's memory through debug mode. The average inference time is 786.73 microseconds. The fastest was 786.58, and the slowest, which is the worst case, was 786.89. So across 1,000 runs, the entire spread is 0.31 microseconds. That's about 52 clock cycles of variation on a 168 MHz processor. The standard deviation is 2.24 microseconds, and that variation isn't random noise. It comes from the fact that different activities produce different data patterns, and those slightly different 8-bit values take slightly different paths through the arithmetic. Walking data and sitting data literally compute a little differently at the bit level. But here's the thing, even the variation is tiny, and this is where the no data cache point I made earlier comes back. Because there is no cache, every memory access takes a fixed number of cycles, so no cache misses occur and no random delays are added. All the memory is allocated statically, so there is no dynamic allocation during inference, and the measurement window can't be interrupted. Putting those three together and the numbers, we can definitely say that the timing is almost perfectly deterministic. For a real-time engineer like me, that's the whole point. With a worst case of 786 microseconds and the task running every 100 milliseconds, the processor is only about 0.79% utilized by this inference task, which means it comfortably passes formal schedulability analysis with enormous margin to spare. So that's the project. The whole project is on my GitHub, the training and quantization scripts, the test sample generation, full embedded project code, and timing results, and complete documentation. The next step I'm planning is deploying the same model on a Jetson or a Nano, moving from a microcontroller to an embedded GPU platform. That is going to give me the chance to compare how the same inference behaves with parallelism across GPU cores. And further down the line, I may also want to explore an FPGA implementation using high-level synthesis, implementing all these operations on programmable hardware to explore parallelism and hardware-software co-design. And before closing, one thing that is worth being mentioning here is that the determinism we are seeing here holds under a specific assumption, which is that the sensor task sleeps for 100 milliseconds and inference task takes under 1 millisecond. That 99 millisecond margin is actually what prevents SensorTask from preempting InferenceTask mid-measurement. There is no explicit lock or critical section enforcing this. It is just a timing argument. If inference latency ever grew beyond this task period, the measurement would be contaminated by context switches and the determinism guarantee would then break down. It is one of the reasons extending this work toward harder real-time guarantees, whether on a Jetson or on a FPGA fabric, will be an interesting direction. If you have any questions or suggestions, you can always reach me through my LinkedIn or email. Thanks for watching.